Good morning, everyone, and welcome to the second last week of Foundations of Algorithms. Given that we're starting to move into some of the more advanced content, I thought today I would bring you a theoretician from our recent history. This is Andrew Yao. He was born in 1946 in Shanghai, and he has not only a degree in computer science, but he has a PhD in physics from Harvard and a PhD in computer science from UIUC. And Andrew Yao is still alive today and happily working on computing. Of interest that while he did a lot of his seminal work in the United States, he actually acquired US citizenship. He renounced his US citizenship in 2015, returning home to China with another very prominent Nobel Prize winner, Tang Ning. Right now, he's the Institute Dean at Tsinghua University and the Distinguished Professor at the Chinese University of Hong Kong. So that's a bit about his background, but what did he actually do? He is responsible for the Dolev-Yao security formalism and the theory of random number generators. Now what this is it's a way to model adversarial behavior in a computer system. So if you have an attacker and a defender, how do you reason about that in a mathematically formal and rigorous way? One of the ways is the Dolev-Yao framework, named after both Dolev and Andrew Yao. For his contributions to the field, he was the winner, much like many of our other historical figures, of a Turing Award, and this was in the year 2000. So there's our historical inspiration for this week. If we get a little bit more ahead of ourselves, maybe we'll even have time to talk a bit about my research and Zhang's research. Mine is in random number generators and security, so very much tied to his work. And that would be pretty exciting. Where did we leave off last week? If you remember, we were asking the question of how many degrees of separation are there between you and the king, or between you and Taylor Swift, or you and whichever other famous person you care to think about. And how did we approach this problem? We constructed a new data structure that was pretty similar to our trees, except we removed the directions of which way the links were going, and then we added more links. So instead of just having 2 links from any node, you could have as many as you like, as many friends as you want, because obviously, I forget who it was last time that didn't have enough friends and we needed to add some more. I think it was either Max or Owen was friendless in a binary tree. Owen was friends with Max and Max wasn't friends with Owen, so we've removed the directionality of these links. We've allowed people to have multiple friends, and then we found a way to get to the king through me, through my high school friend who knows Prince Harry, and then to the king. So this is great. We can now visually see this, but we haven't actually solved it algorithmically. We have a data structure, at least an abstract data structure, but we don't know how to use it. If you have a person that's your starting place, that's going to be the root of your search, how do you actually find how many steps it's going to take you, at minimum, to get to another figure in our graph? So we need a couple of preliminaries. We're going to talk about vertices and edges. So the singular of a vertice is a vertex, and we're going to label the set of vertices V and the set of edges E. And the edges are all these links that we have. Just like we had a link from, say, Max to me, Max and myself are both vertices, and the link between us is what we're going to call an edge. And when we parameterize the runtime of all our algorithms, we want to know, as our graph gets bigger and as we get more connections, how long do our algorithms take to run? So what are some ways that we could actually put this into a program? The first way that we could imagine is just expanding on our node T structure. And let's call this a vertex T. And I could imagine having a new pointer for a node. This would give me room for 3 friends. But there's a bit of a problem in this. What's the problem, Josh?
Well, how do you know how many
take the microphone.
How do you know how many links are in?
Yeah, so this requires me to know a maximum of how many links I'm going to have ahead of time, and then I'm going to have to go through the list and check, okay, is link 1 not null? Is link 2 not null? Is link 3 not null? And as we add and remove people, this is going to become pretty unwieldy, and we're going to be capped by how many links I wrote in there. So what would be another way of doing this? Josh, do we have another data structure that we could use? So thinking about it, I've got a data structure within a data structure. I've got my nodes, well, I should have node T on these. But can I replace these individual node T's by something else?
Yeah, you can use a dynamic array of node ones.
So I could use a dynamic array. And what's another way? Or I could have a linked list. So by combining some of our different structures, so we have our node T struct, which we can use to represent a linked list, or we could embed the entire linked list in there. So now I've got my list T type links, and this is going to contain all the friends that someone has, and we already know how to dynamically add and remove links to a linked list when we have one. So by embedding a linked list within our vertex, we now have a way of representing all the friends that a given person has. So inside, say, my list T of links, I would have a link to everyone else in the class to whom I'm connected. We also still need our data T because we need a place to store my name or my age or whatever other information is going to be associated with me as a vertex. And then we're going to add one more property here, and this will be the visited property. And we'll see why we need this in a minute. And then once I have my data structure nicely collected, I can just make a dynamic array of vertices. So we now have a multi-level hierarchy of different data structures. So we have an array, and it's an array of vertices. And inside each vertex is a list T. And inside the list T is a head pointer. And the head pointer points to a node T. And the node T has data associated with it. So now you can see how we're starting to combine and create a hierarchy of all our different data structures to allow us to solve programs in a more powerful fashion. So you might say, well, linked lists and binary trees, these seem pretty similar to what we've got before. Couldn't we just reuse those nodes? And in fact, you can. You can treat a linked list or a binary tree as a special case of a graph and build multi-purpose data structures as well. However, this will come at a cost. As you make your underlying representation of the data structure in your code more complicated, it'll be more difficult to deal with, and you'll need some way of abstracting out just the details that you care about. And that's what you'll learn about in some later courses, is how to hide away some of the details when you're programming, and particularly for those of you who take object-oriented programming, you'll see a bunch of really powerful ways to just make the program make visible to you as the programmer just the interfaces that you need, just the individual functions from a given data structure that you want to see. So now that we have our initial representation, we've still got our old problem. Okay, we've got our graph. We've now got some kind of representation of it. How do I actually go through it? How do I find the degree of separation between me and someone else? So solution one is to go deep, and we'll do a little walkthrough of this. So with the go deep solution, we're going to start at Owen. Now, Josh, do you want to pass the microphone one way or the other? Giovanni can take it. Okay, let's say we're going as deep as we can. What would be our next step? Starting from Owen, where do we go next? Turn the microphone on. Yeah. So where should I go next? What are my choices?
Left or right?
Well, this isn't a binary tree. Where are all my edges going to? Just read them out for me. Where are my edges going to from Owen?
Max, Phil, me.
Riley and...
Myself.
Yeah, and myself. Okay. So we don't know which of these is actually going to lead to the king eventually. We don't know yet. Remember, the computer only sees one thing at a time. It can't see the whole big picture. So let's pick one of them to go down. Let's say Max. Do you think Max? Okay, let's go down Max. And now we've got a whole new set of edges that we could possibly go down. What are my new set of edges?
Ahmed, Giovanni, Bell,
Okay. Well, we still don't know where the king is, so we're going to go again. Let's go down Ahmed. Still not. We've gone to Giovanni. Now Giovanni has energy drinks and Dr. Connie. I think you know which way we're going. Energy drinks. Okay, let's try going down the energy drinks direction. Unfortunately, energy drinks is a dead end. So what do we do? What should we do if we've hit a dead end?
Go back.
Let's backtrack. Okay, let's go back to Giovanni. And from Giovanni, we go to Dr. Connie. Now, Dr. Connie, let's just pick the high school friend, Prince Harry, and then the king. So through this particular route, we've traveled a total of 7 edges. Now, that does not seem to be the fastest way to get to the king. So our go deep strategy in picking one of the nodes, whichever one we happen to like, to go deep through, didn't seem to get us the degree of separation. However, it did allow us to traverse effectively through the graph. Maybe it'll be useful for some other things. How are we going to implement this particular version, the go deep strategy? Well, we've got our vertex T, we've got our node T, and I'm going to show you some samples. It's a mix between C and pseudocode. We're not providing full implementations this semester, but this is what the go deep strategy looks like. So we have our action that we're going to do at every node. So this would be like check if you found the king or whatever action you want to do at the nodes that you're processing. And now we're going to use this visited element, this Boolean that we have inside every node. And if we've already visited a node, once we visit a node, we're going to mark it as visited before. Why do we need to do this, Yuvani? What would happen? Let's say I have a link to you, you have a link to Josh, and Josh has a link to me, and then I also have a link to my friend Maddie. What's going to happen if I go to you, you go to Josh? What are Josh's options then to go one more step?
We should mark you as linked so that it goes the other way.
Yeah, if we don't mark me as visited in the first place, then we could get stuck in a cycle. Because I'd go to Yuvani, Yuvani would go to Josh, Josh would go to me, I'd go to Yuvani, Yuvani would go to Josh, Josh would go to me, over and over and over, and we'd never stop. So we need to mark a node as visited to make sure we don't go back to that node and visit it afresh. Then what we're going to do is we're going to get all the neighbors of the node that we're currently at. Now, unfortunately, so we have a list of all the neighbors, and then while we're looking at a valid neighbor, mark the neighbor as visited, run DFS on the neighbor, so go deep, repeat the same process on that neighbor, and then move to the next one. And the reason this works is because we're using the computer stack as a way of storing which nodes we're currently at and what were the nodes higher up in our hierarchy. So we can draw that out in a later lecture for you because we're going to go a little quickly today to make time for John. Our other test that we could do is to go broad. So this was our going deep strategy. Now we're going to try and go broad. So Yuvani, do you want to pass it maybe to Callie Rowe because Bruce went last time, I think. Okay, so if I'm going broad, what does that mean to you? If I have my current links of Max, Bell, Nick, Riley, and myself, what should we process next? Possibly all of them. Okay, so if we want to process all of them, we still have to do them one at a time, but we could mark all of them as the next ones in turn to be visited. So let's do that. I mark all of them as next in turn to be visited, and now let's set our counter to 1, because we've gone down 1 away from Owen. Okay, following our strategy, I've gone 1 away. What's the next step?
For each node that you visited, so Max, Bell, Nick, Riley, and Dr. Connie, you would go broad again for each.
Yeah, we'd go broad again. But one more step out, we get from Max will launch out Ahmed, Yuvani, and my high school friend Maddie will also be marked now. So we go broad, and now we go broad again, and so we've marked all the ones that are 1 further, and 1 more, and if we've been counting carefully, we can see that if we count the number of colors, the number of steps we actually had to do, we would have had a total of 4 steps. Now, I see that there was an issue with this slide, so I'll fix that up and get that one out to you. So essentially what we're doing here is we're putting each vertex in a queue and repeatedly extracting the next one to be processed, and making sure that every time we reach a new node, we take all of the links out from it and put them in the queue as well. So starting at the root, we take out all the neighbors of the root, we put them in the queue. Then we take out all the neighbors of the root's neighbors and put them in the queue and process them. And then we take out all the neighbors of the root's neighbors' neighbors and put them in the queue. And by that way, by counting how many levels we've gone deep, we can solve our degrees of separation problem. Let's go here to breadth first search. That's the name of going broad, our strategy of traversing the graph by going broad at first. So this one's a little more complicated. Now, why do you think it might take so much more code for us to code something with a queue than what we did before for depth first search?
Because you have to visit each item in the queue rather than the first one.
So does C have a built-in queue? Or did we have to make our own?
Yes,
And what about a stack? Did C have a built-in stack?
yeah.
Yeah, where was the built-in stack? Yeah, it's in memory. So every time we make a recursive call, we're effectively using the computer stack. And so our code for DFS ended up being really simple because we didn't have to worry about managing the stack. That was done automatically for us. Whenever we made that recursive call, DFS neighbor over there, we were implicitly using memory management as the way that the compiler deals with memory management as our stack. So now that we've moved to a queue, we've got a different data structure. There's no built-in queue in C, and so we have to manage it ourselves. Let's step through the code for a couple minutes and just see what's happening here. But it follows the same idea we just talked about, just with a queue. Okay, so we've got our create the queue, mark the current node, the first node, the root as visited, and then we have a queue push function that we have that will allow us to put a new item onto the queue, and we will also have a queue, oh, there we have, and a queue pop function, which allows us to remove the front element from the queue. So while there are still items in the queue, extract the first item from the queue, do the action, mark that you visited it, get all its neighbors, add all its neighbors to the queue, and do this for all the neighbors. Make sure that you're iterating across all the neighbors and putting them in the queue. So conceptually, we've got a couple of blocks here. We've got the setup block, we've got the extract the front thing from the queue and process it, and then add all of the front thing's children, or all of its neighbors, to the queue itself. So conceptually, quite simple, even though we had to have a little more code in here to actually manage the queue because C doesn't give us a built-in queue. So now let's draw a picture of what our C representation of this looks like. So let's say we have an array of our vertices, and I'm going to label them with the names for our convenience. Obviously, inside the computer, it's not exactly the same. But here is an array of all of our different people that we have. Remember, when we set it up, when we malloced our vertex t's, we had enough room in our array for each of the different vertices. Now, inside each vertex is a linked list. And that linked list contains all of that person's friends. And now what I can do, instead of saying which person it is by their name or containing a complete copy of them, in fact, I can just have a reference to where in the original list of nodes they were. So we can see that Owen is friends with number 1, and number 1 is Max. And if we move to the next item in that linked list, Owen is also friends with 2, which was Riley. And now let's look at Max's list. Max has 0 as a friend, and 0 is Owen, and Max has a friend who's 2, and 2 is Riley. So we have another way of representing this picture using a structure where we have an array of vertices and where each vertex has a linked list associated with it. Now, Calio, do you want to pass it on to Flo? Okay, Flo, this looks like another data structure, though. This doesn't look to me like an array of nodes, each of which has a linked list. Does it look like something else to you? An array, yeah, it's a two-dimensional array. So this is one way of representing our two-dimensional array. And one thing to note here is just that every edge in this representation appears twice. The reason is because if Max is friends with Owen, then Owen is friends with Max, and we need it to have it in both of their lists. Now, Flo said that this looks just like an array, and so let's keep that in mind for a minute, and we might look at a different way of representing the same thing. So I'll just tell you what the runtime of both DFS and BFS are. They both run in big O of the number of vertices plus the number of edges, and they use the space complexity of the number of vertices. So Flo, why do they use a space complexity of O of the number of vertices there are? We're using two data structures. What did we use for DFS? Which data structure did we use for depth first search? We were using the computer's. We were doing recursion, and when we do recursion, we're using a data structure, right? Which one were we using? We were using the stack, remember? We were using the stack. And for breadth first search, which data structure we were using? Yeah, we were using a queue. Okay, so if we're storing our vertices as we see them in either a stack or in a queue, and we have V vertices, how much space do we need? Yeah, we need to store space for all the vertices at worst case, and that's going to be big O of V. So this is the amount of space and time that it's going to take for our current representation. So that seems pretty good. But as Flo just said, our representation really looked like a big matrix. So why don't we treat this as a matrix or as a 2D array and see if we can still run our algorithms that way. So this is another way of representing the same thing, except now I've made it a big 2D array, and I've said, you know, that everyone has 12 possible friends, and there are 12 possible people who have friends. So I have 12 vertices, and each of the 12 vertices can have 12 possible friends, going from 0 to 12, marking each of them with their ID. And now let's just put a 0 in a place where there is no connection between them, where there isn't an edge there, where they're not friends with them. And let's put a 1 where they are friends. So we can still see Owen is friends with Max, because let's make the left-hand column, let's go from the left-hand column, let's go from the first row, we see Owen, and the second column, Max, there's a 1 in there, so that means Owen is friends with Max. Now let's look the other way around. Let's look at Max as the second line, and oh, he's friends with Owen as well, so there should be a 1 in both of those. What does this mean for our matrix? The fact that Owen is friends with Max and Max is friends with Owen, for each friend, should there just be 1 1 in my array, or should there be 2? Yeah, so we should have some kind of symmetry in our array as a result. And if you have a 1 in, say, position 0, 1, you should also have a 1 in position 1, 0 in the array to mirror that, the fact that friendship is reciprocal. So let's fill out the rest of our array. Let's put the zeros back in. And this looks great. We can still run BFS and DFS on this, but we'll need to tweak our algorithms a little to figure out how to extract the person's neighbors. Only now we're a little sad, because instead of an O of V plus E runtime, we're going to get an O of V squared, because we've gone from a representation where we only have a limited number of things connected to each vertex to one where we have to scan through all 12 possible friends each time for every vertex. So not so great. However, there might be some places where this representation would be more useful, and to find out more about that, continue with computer science in the next year. So turning briefly to assignment 2. Assignment 2 is going to ask you to find the intersection between two people's friends and also their union, separately, these two different ideas. So let's go to our matrix representation, because this is a pretty good way of thinking about it. Let's first talk about the intersection of two people's friends lists. And let's look at Max and Riley. So Flo, do you want to pass it on one to Oscar? Yep. So Oscar, let's say I'm looking for the people who are friends with both Max and Riley. Where would I look for that in their rows?
You look, essentially keep going vertically and do an AND operation on them. So perhaps if we have the first two.
I think your microphone's off. Okay, go ahead.
Wrong, clearly. I'm finding it difficult to see the array. So we've got, who are we trying to find?
Max and Riley, who are their friends in common?
Right, so we iterate through each, because we have this nice nice representation where we can look through, for any given person, whether or not Max and Riley are friends, we can look through vertically and then see, well, if there's a 1 in both adjacent or both rows here for any given friend, they're both friends.
So what I've highlighted over here is we've gone for both Max and Riley, we've looked at their Owen column. And in their Owen column, there is a 1 in both of them, which means each of them individually is friends with Owen. Then we go to the next column along. We're in the Max column, and Max is not friends with Max. Max is friends with, okay, so that's a 0 and a 1. Go over to the Riley column, same story. Okay, Ahmed. Ahmed's a new person. Friends with Max, but not with Riley. Okay, not good. We keep going, we keep going, we keep going. Okay, we've only found 1 intersection. What about their union? What would we do for their union?
Same thing, but and or. So if there's at least 1, then we say yes, it's part of the union. If there's 1, 0, 0, 1, or 1, 1.
So we would highlight it as long as we have a 1 in either of those positions. So you can see now that even though Max is friends with Ahmed and Riley is not friends with Ahmed, we've highlighted this column as well. Now, there is a slight catch here, and I'm going to leave this one out for you to solve in the assignment. But you'll notice that if we follow this naively, we're going to run into a little trouble. We might have overcounted in one way. So I'll leave that for you, or maybe for Janjong to cover if he's feeling generous in the next portion. So as a challenge, I'd encourage you to go about and think how you do this with an adjacency list representation. In the real world, we are going to mostly use adjacency lists, And so another challenge is to think about why we might use matrix representations. So unfortunately, in the rest of this class, we are not going to give you the full implementations for these, both because you could choose to do it for assignment 2, but you don't have to. Assignment 2 you can solve using a much simpler way. But if you do want to go into more depth with these, we encourage you to keep taking computer science, and you'll learn all about these in your next algorithms and data structures subject. And so with that, you know what, I will show you a very quick demo before we turn it over to Janjong of breadth first search and depth first search, and then I'll turn it over. So this one. Here we have a nice demo where you can see breadth first search and depth first search being run alternately. So we're going to start off with depth first search. We have a node here with the purple thing and a goal in there. And I'm going to stop this from doing that. OK, so we have a start node here and a goal node here. And from each square, its neighbors are the other squares that are in white surrounding it or that are already visited. Those are all of its neighbors. So let's visualize it. OK, we can see it's going deep. It's choosing one path to go down and going as far as it can down that path. And in each square, it's making a decision which of the neighbors to go down. It doesn't backtrack. It doesn't check all the neighbors of every square. If it crossed over itself, what it means is it had to backtrack at some point. If it ends up in a dead end, then it'll go back and pick a new deep route. Unfortunately, it found the goal this time. There we go. OK, now let's try it with breadth first search. So remember, this was going outwards from the goal, trying 1 square away. Now everything 2 squares away. Now everything 3 squares away. Let's take a look. And if we wait another minute or 2, it will eventually hit the goal. But that should be enough to give you the idea. We are not going to assess you on how you do your own graph traversals or write the code for it on the exam. Don't worry about that. We just wanted you to get a conceptual feel for it, given that it's on the assignment. And with that, I will turn it over to Dr. Janjong for the rest of the lecture.